All right, today we're going to tackle one of the most powerful ideas in all of math, calculus. Now, I know you might be thinking, but forget its scary reputation for a second. Seriously, think of it more like a secret language, a code that describes how pretty much everything in the universe moves and changes. From a planet's orbit to the stock market, calculus gives us the words to understand a world that's always in motion. So let's jump right in.
To get us started, just think about something you see all the time, your car's speedometer. When you look down, it's telling you your speed at that exact instant. Not your average speed from the last few minutes, but your speed right now. But how? I mean, how can you even measure speed in a single moment that has zero time? Well, the answer to that little bit of everyday magic is calculus. So our journey really kicks off with this one big idea, the mathematics of change. And to really get a handle on it, we need to understand three core concepts that all build on each other, one by one.
And here they are, the three big ideas. First up, we have limits. These are all about getting super infinitely close to an answer, especially when you can't get there directly. Then we have derivatives, which use that idea of getting infinitely close to find a rate of change in a single instant. And finally, integration, which is kind of the reverse. It's about adding up a ton of tiny little pieces to see the whole picture.
So let's start with that foundation, right? Getting infinitely close. This is the whole concept of limits. A limit is really just a clever way to find a value when you can't just plug in the numbers and calculate it. It's the tool that lets calculus deal with situations that at first glance seem totally impossible. So, for example, what if you have a function where plugging in a certain number, let's just say the number 2, gives you a total mathematical roadblock, 0 divided by 0? I mean, what even is that? It's undefined. We're stuck. We can't calculate it. This is exactly where limits come to the rescue. Instead of trying to land on the answer, we're just going to sneak up on it and see where the function is heading. And here's how we do that sneaking. Just look at this table. Instead of plugging in 2, we're trying numbers that are just ridiculously close to 2. So if we plug in 2.1, the function spits out 4.1. Okay, let's get even closer, like 2.01, and we get 4.01. You see the pattern here, right? The closer our number gets to 2, the closer our answer gets to 4. And that is precisely what a limit is. It's the value a function approaches, even if it can never technically land right on it. So for our little problem, even though the function is undefined at 2, the limit as we get closer and closer is clearly 4. Limits give us a way out of these otherwise impossible problems. It's pretty cool. Okay, so now we have this really powerful tool for getting infinitely close. We can use that to go back and tackle our original speedometer problem, finding the speed at an instant. And this, my friends, is the world of derivatives.
So the key thing to get here is the difference between average and instantaneous. As you can see, a secant line just connects two different points on a curve. That gives you the average rate of change between them. But a tangent line just barely kisses the curve at one single point. And its slope, that's the instantaneous rate of change at that one exact moment.
So how in the world do we find the slope of that tangent line? Well, we start with a secant line that connects 2 points. Then we start sliding those points closer to each other and closer until the distance between them is infinitely small. Hey, does that sound familiar? Of course it does. We're taking a limit. By using a limit, that secant line basically transforms into the tangent line.
This chart shows you exactly what's going on with the numbers. When our 2 points are far apart, the average slope is, say, 13. As they bring them closer together, the slope gets to be a better approximation, maybe 12.01. And as that distance between them approaches 0, the slope just zeroes in on the true instantaneous slope of that tangent line, exactly 12.
And that right there is what a derivative is. It's the tool for finding the exact slope of that tangent line. It gives you the precise, instantaneous rate of change for any point on your original curve. It's literally the math that tells your GPS your speed.
Okay, so we figured out how to break things down to see the rate of change at one instant with derivatives. Now for the final piece of our calculus puzzle, integration. And if derivatives are all about breaking things down, you can think of integration as putting it all together.
Really, the simplest way to think about it is just this. Integration is the opposite of differentiation. They're two sides of the same coin. If differentiation is like zooming way in to see the change at a single point, integration is like zooming way out to see how much has been collected in total.
So yeah, just like it says here, a derivative breaks things down, integration builds them back up. It's all about summing up all those infinite tiny moments to finally get the big picture. And a great way to visualize this is by finding the total area under a curve. Here's a really simple way to keep them straight in your head. At its heart, finding a derivative is kind of like division, right? Slope is rise times overrun. Well, finding an integral is kind of like a multiplication. Area is height times width. They are perfect opposites.
Let's make this real. Imagine water is flowing into a big tank, but the rate of the flow is changing over time. Now, if we want to know the total amount of water that's in the tank after, say, 80 minutes, how would we do it? You guessed it, we integrate. We find the total area under that flow rate curve.
And the answer is 4,000 gallons. By integrating that rate of flow over the whole time period, we find that a total of 4,000 gallons of water have collected in the tank. But how did we actually calculate that number?
You know, it's actually way simpler than you might think. This area under the curve can often just be calculated by breaking it into simple shapes we already know from geometry class. The area of the rectangular part at the bottom, that's 2,400 gallons. And the area of the triangle on top, that adds another 1,600. Add them together, and bingo, you get your 4,000-gallon total. That's integration in action.
So, we've walked through the three big pillars: limits, derivatives, and integration. But let's be honest, why does any of this actually matter outside of a math class? Well, as we're about to see, this stuff is absolutely everywhere in your world.
Derivatives, that's the tool for rates of change. They're used for everything from figuring out a rocket's trajectory to modeling how the stock market might fluctuate. And integration, the tool for total accumulation, that's essential for things like calculating the correct dose of medicine over time or creating realistic 3D graphics in video games. Together, they really are the language of change.
So the next time you see the perfect arc of a ball flying through the air, or a graph showing economic growth, or just the speed on your dashboard, you'll know the hidden language that's describing it all. You've just learned the fundamental ideas of calculus. So the real question is, now that you speak the language of change, what are you going to see differently?